FDP, HTTP about technology and science. I will first introduce Dr. Arpon Deoshi sir. Dr. Arpon Deoshi is presently working as Associate Professor in the Department of Electronics and Communication Engineering in RCC Institute of Information Technology, Kolkata. He has more than 20 years of professional experience in academia and industry. His work spans around in the field of semiconductor nanostructure and semiconductor photonics. He has published more than 200 peer-reviewed research papers and edited 11 books and one in press. He has completed 500 projects as PI and co-PI. He has already served as technical consultant of various industrial projects. He is associated with different international and national conferences in various aspects and also serving as guest editor of a few renowned journals. He is senior member of IEEE, chair of IEEE Electron Device Society Kolkata chapter, fellow of IEI, IET, ISB, etc. He, along with his research group, received so far 7 times Best Paper Award in various conferences of repute. That is all about the introductory part of Dr. Arpon Deoshi sir, who is the speaker of today's HTTP. Okay, sir. Thank you, sir.
Thank you, madam, for your elaborative introduction. Very good afternoon to my all dear colleagues. Actually, so let's make a journey today. I think there will be a heterogeneous structure for today. So for that, I know that if there is a heterogeneous structure, then a discussion would be carried out in a some sort of mode where we should. I think my screen is properly shared. Is it visible, madam? My screen. Oh, thank you, sir. So I am trying to make a topic of discussion which will myself also in the nascent working in the field 2 years with my research scholars and students of UG and PG level. And this is one of the domain which I am trying to highlight because already AICTE introduced this topic as a minor under NP and across all streams. Any EG program, whether CS, IML, EC, electrical instrumentation, can go for their B level or UG level minor, and then along with the major, they can provide a minor degree. And the work is actually vast area. It's open several seeds of opportunities available. So let's try to make a jump within that enlarged sea and why this topic is so much important nowadays. Let me start with, as a engineering background student, consider we are forget about what is our domain of working and anything else. We most generalize some sort of engineers. We know what are the security threats in the classical computing, and we are very familiar with DDoS attacks, data breaches, inside threats, weak passwords, social engineering, everything we are very familiar. And several precautions we are taking, but still in everyday's newspaper, online, social media, and some news, we found that there are several vulnerabilities available. So, would be the responsibility of the technical people moving to a perspective where encryption problems should be unbreakable, threat detection is in advanced level, authentication should be in hack-proof, and data recovery will be instantaneous. Is this possible? Then I think the left-hand side features can be easily vanished. Let's move towards the technology of the quantum computing, where the privacy and security concerns are very important for making any step. We are mentioning here what are the risks of the data breaches today. It's we require a robust security measurement, but for which the hardware and the hardware cost and software complexity is enormously high. Is it possible to implement quantum extension method where, based on the user consent management and obviously by the government's uh, compliance regulatory authority, can put this enhanced security and data protection laws? Because whatever be the engineering stream, engineering discipline we are much concerned about day by day. We are using Google Pay, Paytm, PhonePe every day. And we have to be very cautious what we are scanning, what we are transferring. The largest digital uh, monetization is now in India. So based on this, we have to see from our journey from bit towards the qubit. But saying is easy. The difference is that there are some major challenges in the qubit. One is the decoherence, because the measurement of the state makes it collapse of that state, and there will be huge external noise. Saying is very easy, theoretical perspective is easy, but practical point of view, accuracy, the disruption of the state, collapsion of the state, and the huge amount of the external noise. Whether could we move from the theoretical quantum computing perspective to the practical quantum computing, which can be used in our database? That will be the query, that will be the question today we are making step by step. So, a minute. So this is the point where we are basically thinking about that theoretical quantum computing is okay, fine, well known, but practical point of view, the quantum computing are really a prioritized thing. So let me move towards a video. কোন সুইচ বোর্ডটা ওই সুইচ So that is the spooky action at a distance. And if you know the famous scientist of Richard Feynman, he said that by shaking your finger, you can discover the universe. So that is the concept of the entanglement. That means everything is square, entangled. Let's come to our daily domain. Why I am considering such a abstract level response into our real world of classical algorithm and how it can be fitted. Look, I am just giving a 2x2 matrix of the data type with the algorithm type. If data and algorithm both are classical, then we are considering quantum inspired classical algorithm. I will come into the actual the algorithmic part a little bit later. I will show the details mathematical description how the algorithm will work without going to any text or something representation, some sort of textual representation. I will just go through the numerical calculation which we can solve using a pen and paper a little bit later. If it is quantum, then classical algorithms can be applied into the quantum. No problem. Point is, if the algorithm is quantum, then quantum is the classical algorithm. Again, these two are similar. Or we can work either this. So these two are the points where we people can play our role. So what are the practical risks of the quantum algorithm? Problem is that if you plot a likelihood with the impact matrix, if the likelihood, whatever be the likelihood, the impact will be minor or moderate if there are data errors, negligible or hardware failures or inaccuracy or small privacy breaches we can have. The point comes in the picture of ours when the point is going for a ethical dilemma. Ethical dilemma is a huge factor. Uh, Ethical dilemma is a huge factor which decision we have to take. That people are mostly difficult finding it. The critical breaches in the data security, that's mostly the financial, share, and some sort of cyber security cases, the potential hazard in the defense application. And the last point is that unprecedented ethical violations which we have to be avoided, and for which the quantum computing the guidelines are extremely difficult. So there will be some historical evaluation of the quantum computing. I am not going into too much because in 2025, people are looking for superconducting quantum dots and coupling with that. So far, we can progress forward. But let me come into this historical evaluation a little bit later. I will come to the last part of this when we have covered everything. Now comes to the present implementation challenges as we from our engineering institutes what we will face once we go for the hardware in the form of photonic benches or photonic benches along with the implementation of the algorithm. The first thing we have to consider that the qubit decoherence, they are extremely fragile and lose information. The error rates, quantum gates and measurements are error. Scalability, increasing qubit count, that controlling is extremely difficult. I will show the logic gates with the corresponding mathematics. And most important, I will move towards the quantum cryptography, where we will show that how these things are going forth. The power energy cost, extreme amount of pure water is required for the cooling part. Compilation challenges because the abstract algorithms if efficiency onto the noisy hardware is non-trivial. On precision, extremely accurate timing that is required. The clock should be ultra pure and ultra fast. The cryogenic infrastructure complexity. This is not playing with the liquid nitrogen temperature much higher than the 77.4 Kelvin. Maintaining that temperature in lab is extremely difficult. So people are moving towards the chambers. So I'm considering the lab activity, the chambers. So these things are fitting. So how we can implement in our domain, in our day-to-day life, this overcoming these challenges. Let's So now we are considering towards moving towards the first point of the practical implementation is the key distribution, and this is very important in the 2025-26 academic year. I will come at the last point of the discussion. So what are the ethical considerations what I am talking about? The first point is the bias in the ML algorithm. Second is the privacy issues, that unauthorized data access and personal use of data. Environmental impact, energy consumption in computing systems and sustainability. Accountability, responsibility issues, difficulty in tracking decision-making processes. These are the points where the ethics will play an important role. So how much energy consumption should we allow? What will be my responsibility boundary? How difficult in tracing the decision making? How fast we can take a decision? How it will help me to prevent any misuse? And then the making the outcome neutral. That is the most key factor in the quantum. Theoretical is perfect, but practically making a neutral bias an outcome is independent of bias is extremely. So without going to that, let me come to the what are the industry specific challenges. Why I am doing with my perspective is to find out the challenges, and let me go starting from the very basic level of the logic towards the cryptography, towards the algorithm, to finally lead us the conclusion. So strength will be large data processing capabilities. That's the advantage of the quantum, and you know the IBM quantum already developed a lot of algorithms and working towards that. This is complexity of algorithms create ethical oversight. People are not considered or bothered about too much the ethical factor so far. Threat, biased data set. If the data set is biased, no quantum hardware will give you the perfect result. But there is an opportunity of the emerging market, and you find that some of the renowned central government institutes as well as starting from the private institutes from this academic year started quantum science and engineering as PG level as well as UG level. BTech in quantum science and engineering, MTech in quantum science and engineering. So I have previously mentioned as a minor degree of quantum, but now it comes to major in quantum. And probably 2030, we will get the first batch with a major in quantum category. So people are already developing. AICT has taken a lot of initiatives, and maybe the next 20 years will be the world of quantum. So present state what we are. Now in our lab, we can't work on the ion traps or superconducting qubit, but we can try to simulate semiconducting qubit and photonic quantum chips. Or we can try to make a photonic beam-based hardware by bending of the light and try to analyze that information with our quantum world simulation. So the EC people can play a great role, precisely those who are working in the domain of photonics, and can map your algorithmic result with that, but that will need some sort of infrastructure. And National Quantum Mission is basically directing towards that. So I am coming to that hardware technologies now. From algorithm and hardware, with that gist, I will make towards my impact towards the logic gate from the initial level. So what are the hardware technologies available? First is the quantum processing unit substrate, the physical chip that can connect the qubit. Second is the control electronics, the laser, RF generator, what I am talking about, the photonic ranges, and DAC ADC converters. Photodiodes, resonators, detectors, convert quantum state to classical signals for your measurement, because you can't measure in the quantum domain. Please always remember that factor. You can't measure in the quantum domain. You have to convert quantum states to classical signals in order to measure those. Then there are cryogenic and vacuum systems if you have to reach the industry perspective. Cryostats, vacuum chambers. You may work with your lab in the waveguides, optical fiber, microwave buses for coupling qubits. Then we are going for clocking and synchronization systems, precision timing hardware, error correction and feedback hardware, and sealing and minimization. These three are basically the part of the instrumentation. The synchronization of the system, the communication and the instrumentation people, they are going for the clocking. The error correction feedback, this is the ancillary support, so the marks and corresponding analysis. The problem people are toward focusing the reducing of number of ancilla. I will come a little bit later. Graphical feedback loops and real-time controllers. Then the magnetic shielding. If you look out the quantum materials, people are learning and developing the curriculum. The role of paramagnetism, diamagnetism, ferromagnetism, the materials are extremely important. Is there any? It's working fine. So, thank you. If you have any queries, please write in a chat because I am making a full screen. I can't answer right now, but I will obviously try to handle the queries. And then the calibration and diagnostics hardware, the oscilloscope, the monitoring system generators, and CPU, GPUs, and high quality FPGA boards. NVIDIA GPUs are basically made apart for this quantum hardware. So these are the hardware technologies. Now I am going to So with that basic concepts of the communication which we have said, I will at the end of how India have developed the hardware and what communication is. Now I am starting from the first. So that is my introductory part of this lecture where we are showing what are the data breaches, what are the security concerns, what are the ethical dilemmas, and what will be the quantum entanglement based on which we have to proceed for. Now I'm starting as the textbook sort of progression, starting with the fundamentals of the quantum logic, because we have to solve the existing problems as much as possible. So quantum gates are fundamentally operated than multiple qubits that is an analog of classical gates. So there are two sort of operations. One is called the reversible operation, another is called the unitary analysis. So every quantum gate can be undone, reserving the information, and that preserves quantum state probabilities that will be represented by unitary analysis. Let's go for what are the logic gates for this part of entanglement calculation. First is the Pauli X-gate. That is the famous of Pauli. Pauli X-gate where the diagonal elements are 0 and non-diagonal elements are 1. So what is this? Flips qubit only without affecting phase. Please look out this last part, phase. The phase will play the most critical role while going for the quantum entanglement communication. So if I have a 0, it is the upstream, 0 is represented by 1, 0, that is a simple matrix. And if we calculate, we will get 1. And if we apply on 1, which is the downstream, we will get 0. So Pauli X-gate basically makes a conversation between 0 and 1. So we can consider as a NOT gate. So if I have a generalized psi, that is my wave function, which can be represented as alpha 0 plus beta 1, then at Pauli's X-gate, we can get alpha 1 plus beta 2. That means it is basically reversed. The next step is the Pauli block. Flipped qubit with shifting phase. That is the difference with the prefix. The diagonal element remains 0, the non-diagonal element becomes minus I and plus I. Let's verify it. Apply on 0, you will get 0I, that means you will get I1. Apply on 1, you will get minus I0, that means I0. So Pauli Y-gate, when applied with the G state, it will give I1 state. Applied with the 1 state, it will give the I0 state. So generalized equation for Pauli Y will be alpha 0 plus beta 1 or alpha I1 plus beta I0 when applied on that. So this is my second gate. Now I am considering basic gates. I will slowly increase the quality. Now I am going for Pauli gate. It has a beautiful tendency, it never flips qubit. So why it is what? It flips the only phase. That means diagonal elements becomes 1 and minus 1, or diagonal elements becomes 0. So when it is applied on the 0 state, it will give 0. When it is applied on 1, it gives minus 1. So alpha 0 plus beta 1 will become alpha 0 minus beta 1. So it flips the phase only, not the magnitude. Alpha and beta will be the same. So this is the Pauli gate, that is the first level. I am going to the next hierarchy, that is the Hadamard. And Hadamard is the most crucial for understanding all those sort of principles. It creates equal superposition states from the basis states. Its matrix is defined 1 by √2, that is the normalization factor. Only the minus 1 appear will be. Let's apply on Hadamard on 0. You will get 0 plus 1 by √2. If you apply on 1, you will get 0 minus 1 by √2. So Hadamard gate will provide the values of 0 plus 1 or 0 minus 1. That will be the on the basis states. So generalized equation will be alpha 0 plus beta 1 if I apply the Hadamard. Naturally, zeros will be alpha and 1 will be beta. So 1 by √2, alpha plus beta 0 plus alpha minus beta 1. That is the Hadamard gate. Next I am coming to the T gate. T gate has a beautiful tendency that it applies a phase rotation of 45 degree to the 1 state. So look, 0, it is 1, 0, 0, e to the power I pi by 4. Now look, we are directly involving phase. The term will be e to the power I pi by 4. So T0 will be 0, but T1 will be, look, this term with me. That means we are making a 45 degree phase e to the power I pi by 4 phase change. So it has a peculiar nature, it will not affect any 0 state. Now I am giving a simple problem based on that. Suppose a quantum state is given to you, and you have never told what is the particular state. You have to choose a gate by which you can easily identify the existing state. Simply apply T gate. Because if the existing states remains unaltered, it will be 0. If the existing states makes a phase shift of 45 degrees, it will be 1, as simple as that. So the generalized equation will be alpha 0 plus beta 1 and alpha 0 plus beta of this 60 per I pi for 1. Apply on the wave function. Next, I am coming to the S state. S state makes the same change but pi by 2 radians. Look, S0 applied, it will give 0, but S applied on 1, it will give I1. So I makes pi by 2 change. Sine to cos or cos to sine. So an S gate will give you a notation of the change of phase. The vector will shift. I will show the photonic vectors, photon vectors in it few slides after. So S0 and S1, S gate is another gate which will give you the phase rotation of 90 degrees. So again, if I come back, I will obviously go for more gates, but Px, Py, and Pz is a one type of gate. Hadamard is the extremely important, extremely crucial, totally different types of gate. And P and S are basically dealing with the angular shift, whether it will be 45 degree or 90 degree. Next comes to the rotation gates. Rotation gates means, first I am coming to R, I will for Rx, Ry and O. Look the blocks here. Rotation, if it is along this, I am showing with my mouse pointer, if it is along this, the red dot I think you are seeing, it will be called x-axis rotation. In this particular direction, it will be called x-axis rotation. So it is basically used for creating superposition or adjusting the space. And look out how these rotation gates are determined. The cos theta by 2 the diagonal elements and minus I theta by 2 are the off diagonals. If you come to rotation 1, then I am coming to the calculation first. Rx theta on applied on 0, it will be cos theta by 2 0 minus I theta by 2 1 as usual. And if you apply on 1, it will be minus I theta by 2 0, it will be crossed and cos theta by 2. This is the action on the basis space. So what will be the generalized equation? Generalized equation will be, if you apply on alpha 0 and beta 1, you will get like this. Now look out the bottom part which is written in the yellow box. I am considering the phase as this theta will be 5. If you put theta as 5, you will get Rx is equal to minus Ix. What is x? This x is the Pauli's x. Pauli's x. So that means if I apply rotation gate with a pi phase change, it will give me the Pauli x. This is one of the biggest conclusions please try to assume. If you apply pi phase shift on a rotation gate x, it will give you the x, Pauli x. Now I am coming to the rotation gate y. Instead of this sort of rotation, I am going in this direction. So Ry gets rotates the qubit state vector on the block sphere. Its purpose is creating or superposition or adjusting it as usual. Look here, the minus sign is missing. Sorry, the I value is missing. Sorry, from the off diagonal, look, the I value is missing. And another change is this becomes also positive. So R will have a different off diagonal element. Rx has the same off diagonal. That's the basic difference between the Rx and Rx. Let's apply this state 0. Ry 0 will give you cos theta by 2 0 plus sin theta by 2 1. Ry 1 will give you minus sin theta by 2 0 plus cos theta by 2 1. Because of the change of sign here, also the change of sign comes. So this is the Ry sum. So Ry generalized. This is alpha beta. I am not going into that. Ry, if you apply the same pi phase shift, it will give minus Iy. That means Pauli's y. So please now Rx pi is equal to x gate, Ry pi is equal to y gate. That means if you don't have Pauli x or Pauli y, you can construct it using Rx and Ry respectively by applying a particular phase. That's the important thing. You are creating Rx and Ry by applying a particular phase, and Rx becomes x and Ry becomes y. Now I am coming to the rotation on the z axis. Look along which direction it is. It's rotating along this. So this is also has the same purpose, but now look, off diagonal becomes 0, diagonal becomes e to the power I by t. So Rz when I am applying 0 e to the power minus I theta by 2, Rz applying to 1 e to the power I theta. And similarly, Rz applied with a pi, it will give you z. So this is we call the back to the square one. We have started with Pauli x, Pauli y, Pauli z. We have covered Hadamard. We come to the rotation gates, and once applying a particular phase shift on the rotation gates respectively, we are getting back Pauli x, Pauli y, Pauli z. So that's the basic thing, that rotation gate effectively helps to obtain the fundamental gates. So Rz pi by is this, Rz pi by 4, look, it will give you T gate. That is another advantage. If you consider pi by 2 instead of pi, if you consider pi by 2 rotation on Rz, it will give you S gate. That I have already covered. If you apply pi by 4 on Rz, it will give you T gate. So may I consider Rz as a universal quantum gate? Do you agree? Because Rz applied on 3 different phase values, pi value will give you Z, pi by 2 phase value will give you S, pi by 4 phase value will give you T. Could you find that your digital electronics concept is represented in different matter? Obviously, all calculations will be based on matrix. You are taking a different pattern. So Rz, Ry, Rx, they are giving the Pauli Z gate, S gate, and T gate for applying different phases, pi, pi by 2, pi by 4, like that. Now I am coming to the controlled knot, C knot. This is one. Now look the matrix side. It's 4 by 4. And it is not the diagonal, it is basically your some sort of gray code sort of format. 1, 1, 1, 1. Like this is C naught. Now C naught applied on 0, that means 0, 0, because it is 4 by 4, you have to consider 2 by 2, so that you can make the matrix multiplication will be 0, 0. C naught applied on 0, 1, you will get 0, 1. C naught applied on 1, 0 and 1, 1, look these are. If I apply C naught on 1, 0, you will get 1, 1. If I apply C naught on 1, 1, you will get 1, 0. So C naught is the first complete gate I am shown with a 4 by 4 matrix. Where, because of this sort of matrices, only these two will be solved, but previous these two cases remain the same. C naught gate exchanges the third and fourth state, not the first and second. The beauty, look, we are considering alpha, beta, gamma, delta. Only gamma and delta corresponding states are changed. Alpha and beta corresponding states will be changed. So that is the controlled knot. Next, I'm coming to the show up. 2-qubit quantum gate that exchanges the state of 2 qubits without changing their computational basis. Now look the change. 1, 1, 1. Like a S format. Could not you find some sort of S value? If swap it, so it will basically swap between second and third. So 0, 0 will remain 0, 0, but 0, 1 will become 1, 0. And similarly, 1, 0 will become 0, 1. 1, 1 will remain 1, 1. So that's the swap. At one point, I request all the learners who actually have not worked till date, those I am calling, but they will, obviously I know that they will work and they will contribute significantly. Swap gate and S gates are not same. S gate has a 2x2 matrix, lower level gate. Swap level is a much higher level gate. It has a 4x4. Don't write swap means short from S. If you write S, this is 1, 0, 0. That is the phase rotation of pi by 2. But the swap is totally different. This is my C0 and this is my swap. So swap basically changes coefficient between the beta and the last time coming to the Toffoli gate. After that, we will go towards the algorithm and the photonic implementation of crypto. The Toffoli gate is called controlled C0 or C0. Or some textbook write a C square naught. You may write in that format also. Toffoli gate sometimes written as C square naught. So it is called controlled knot. The 3-qubit quantum logic gate is its third qubit is fixed. When both the first 2 qubits are in state 1, mind it, if one of the qubits, both of in the state 0, the third will not be. Third qubit, 3-qubit quantum logic gate, the third, that is the third qubit will be fixed when both of the first qubits are in the equal state. Have you mapped with your digital electronics combinational circuits? This is the difference between the, now look, the Toffoli becomes 8 by 8 matrix. So this expand the Toffoli gate. Apply on 0, 0, no problem. The problem will come the 9th and 10th. This is fine. Look here. 1, 1, 0 become 1, 1, 1. 1, 1, 1 become 1, 1, 0. The 7th and 8th, they are changed. And if you simply multiply, so this is the all 10 logic gates we have considered for our next set of problems. So once the logic gate part is over, I am showing hopefully as a notation. I am not going to that. Now I am coming to the algorithm. So one have any query in this point? Or we can collect the queries later. Okay. So now I am going to the first algorithm, that is the source algorithm. And that is the quantum computing's first of it. So what Peter so did and what is the problem first here? The classical limitation is that factoring the super polynomial or sub-exponential. So large number factoring computationally infeasible. What Peter showed in the Bell Lab in 1994, the factors large integer in polynomial time. What is about that? But the problem is the threat to the RSA encryption factoring by solving factoring problem. So how this factoring problem is let me go to the, before going to this slide, I am coming to here. Please, I request all of you to look out this factor. Suppose you are given a number 15. Now factor. School level, we learn that 15 is equal to 3 5. As simple as. It's a number A such that 1 less than A less than A. Let's consider A is equal to 2. So what will be the GCD of 2 and 15? A comma N. That means the greatest common divisor. 2 and 15 will be 1. Now, source algorithm finds the period of fx as a to the power x mod n. That is the formula. What source developed? The period will come a to the power x mod n. So 2 to the power x mod 15. Put the values. Now, how could we get substitute? X is equal to 1, 2 to the power 2 mod 15 means 2. X to the power 2, 4 mod 15 means 4. X to the power 3, 8 mod 15 means 8. X to the power 4, 6 mod 15, that means 1. Again 5, 6, 7, again 8, 1. So this is the x and 2 to the power x mod 15, that's the table you have to keep. Now, after which value the first repetition comes? 4 values. So value repeats after r equal to 4. If you get r is equal to 3 and 5, then your calculation is wrong. Source algorithm requires r should be infinite. So next, yes, please.
হ্যাঁ বান্ধবী হলুদ চুল পরে বান্ধবীটা বান্ধবী কি করবে দেখ বান্ধবীরা কি করবে মারা না এখন ওকে দুধ চালাতে ঝোলানো হ্যাঁ হ্যাঁ
So once r is equal to 4 we are getting, then put a to the power r by 2 calculated, so it will be 4 and it should not be minus 1. Source algorithm requires, this is the condition, that a to the power r by 2.
হাই সব দেখাচ্ছি না
So it should not be equals to minus 1. So that's the period will be. The formula is you have to calculate GCD of a to the power r by 2 plus minus 1 comma n. Now put r is equal to 4. So a to the power r by 2 is basically 4. So 4 minus 1 is 3. 3 comma 15 is 3 and 4 plus 1 5 is 3. These two are your factors. You will get final result 15 is equal to 3 into 5. Now you can take a large number 127 into 120. Choose the same factor, you will get the values as 127 and 129 if you calculate the GCD. I am taking a very small number so that we can identify, but this is the way source algorithm basically works. So once this works, so I am coming, this is basically RSA encryption secures everything from online banking everywhere. There will be for extremely large prime numbers, it is extraordinary. Source algorithm solves that. It uses the superposition of the states and simultaneous function evaluation so that you will get the entanglement enhanced parallelism. That means these two GCD values we are obtained after taking the GCD, they are correlated. These factors are correlated. So this is basically source algorithm. I am not repeating this. So what is the difference with our existing algorithm? Existing algorithm, our bits computing are 0 or 1. Source algorithm is going for qubits. Core principle, this is the sequential or classical or parallel computation. This is the quantum parallelism plus interference. E operations, many factor combinations. This is the period fx is equal to e to the power x mod n. Time complexity, this is sub-exponential, this is polynomial time, conventional CPU, large-scale fault-tolerant quantum computer, RSA is secure, RSA can be broken. That is the first breakthrough so published in 95 probably, the paper where RSA can be broken. Large chain, we can't use classical algorithm, we can use effectively for very large infrastructure. The next development is made by Grover. What is that? Classical search problem, if you go for this heuristics analysis, searching an unsorted database basically requires, if there are n number of items, then n by 2 set of queries. If n is crores, then you require 1 crore by 2. Finding phone number in a random phone, book in an unsorted bookstore, card in a shuffled deck. So classical search scales linearly with database size. Time complexity is O(n). As dataset grows, with the search time proportionally grows. Quantum advantage is that the quantum computers leverage cubes and superposition to process many states simultaneously. The Grover's algorithm proposed by Love Grover, he basically make a quadratic speed up. Instead of O(n), he make O√n. Now, if you consider classical search need of 5 lakh queries, Grover's algorithm need 1,000. Those people who are very familiar with making queries, SQL, the database, or DDS sort of things, you know that beauty of O(n) and O(n). How it is important for an extremely large database, precisely when the database is not sorted. So that breakthrough from the time domain given by the Grover. So I am going for the Grover's in a depth. Suppose I am typing 8 items, n is equal to 8. N is equal to 8 means 2 to the power 3. So that means 3 qubits. My target state say that means we are going, if we consider 3 qubits means we are moving from 0, 0, 0 to 1, 1, 1. Suppose my target state is 1, 0, 1. It will be my target state. So initial state is 0, 0, 0. Apply Hadamard git to each qubit. You will get this expression naturally 1 by √8. X is equal to 0 to 7. Your oracle splits the phase of the target. Only the 101 will become minus 101. Others will remain unchanged. So from 0, 0, 0 to 1, 1, 1, only 101 will be filled. So what is the beauty? The probability of measuring target after first iteration is 0.78. You have already reached in the conclusion. And how many iterations required? The formula is pi by 4 √n. So if n is equal to 8, pi by 4 √8 means 1.98. So second iteration will give you the result 0.995% accuracy. That means 99.5% accuracy. You don't have to go for third iteration. Classically, we require 8 iterations. Quantum mechanically, we are requiring 2 iterations. Now consider n equals to 64, say. So classically, it is 2 to the power 6 qubit. You require iteration pi by 4 √64. That means only 2 pi. That means 6.28, maximum 7 iterations. Instead of 64, you require 7 iterations. This is the beauty of the Grover's algorithm. As you are going for more and more classical iterations, quantum iterations drastically decrease. So again, I am making a difference between the classical algorithm and Grover's. Classical algorithm data success is sequential, Grover is parallel. Search strategy trial and error. It is the amplitude amplification. It will just give a delta function. Others will remain 0. Hardware is the classical bit where hardware is the qubit, time complexity, O(n) and O over n. Now I am coming to the cryptography, how it will lead towards some cryptographic method. So we are considering now the horizontal and vertical photons. I think these two pictures are quite clear. These horizontal and vertical photons in our photonic hardware setup, we will call as the rectilinear basis. And these angular photons are left or right plus minus 45 degree, because this will you will not consider 360, it will be 180 we will consider. And this plus minus 45 we will call as a diagonal basis. Now look, what are the spin theories? If you rotate in this direction clockwise, it will be called spin up. If you rotate in this direction anti-clockwise, it will be spin down. Spin up will be 0, spin down will be 1. And look how the upper thing works. 0, 0. So two things. 0, 1, 1, 1, and 1, 1. So these are the pluses and minuses we have to consider based on this spin up and spin down. I'm not going into CMOS comparability, but comparing between sender and receiver. Suppose you have a 0. You have a 0. Once you want to send a 0 with a particular sort of, say, analyzer, you will get a upspin. Same analyzer, you will get 0. That is the Alice basis. This is your box basis. That is the same basis state. And you have a 100% flow. But once you have a 0, your Alice basis and the box basis are different, then it will be have a two probability, 50% of 0 and 50% of 1. That means Alice and box basis are different. So the 0 will not give you 0 or 1 if the bases are different. 0 will give you 0 if the bases are same. So this is the comparison between the sender and receiver. So what is the basis of encoding? This is 0 up, 1 is vertical, horizontal, that is my plus basis. If 0 is upward, 1 is downward angle, this is I am comparing as a plus basis. So look the video. So I am coming to the protocol. Now look, Alice is sending a bit 0, 1, 1, 0, 1, 0, 0. So 0 means plus 1 upward. This 1 cross. I am sending a random basis plus and cross. So if 0 and plus, it will be horizontally upward. 1 and plus, it will be down step. 1 and cross down. 0 plus up. 1 cross down. 0 cross up. Like this. That I have already seen. God doesn't know what is the photon polarization of the Alice. His random measuring basis should not be Alice measuring basis. You can use plus, cross, whatever, blah, blah, blah. So Bob's photon polarization will be 0 and plus this upward, 1 and cross downward, 1 and cross downward, 0 and cross horizontally like this. Now please check which are matched. Only the photon, not bit. These two matched, these matched, these two matched, and these two matched. Just transfer them. 0, 1, 0, 1. This is your result of it. You can't get anything about it. So you have a probability that you are getting part of the bit 50. So whatever Eve is trying to destroy, you will get this portion in program. That is the way of transferring, and that was discovered by Barnard and Brassard. I am going into this, that is called process of quantum key distribution. Without going into details, the mathematics, let's look at Alice Sender send the stream of photons. Uses beam splitter to read the photons. Now, when it informs which photons were read correctly, Bob as the key receiver detects Alice which polarizer used. Alice and Bob's using the same sort of polarizer. So it can detect odd bits and can detect the eavesdropping. He or she can try to make so many things but can't get actual things because these things are eavesdropping. Yes, the classical communication channel makes alpha 0 plus beta 0. This is the Alice and Bob's. This is the quantum pair. It will be introduced in this format 0 cross 0 and 1 cross 1 with a normalization factor 1 by root 2. So without going into, I am not going into the mathematics of the quantum cryptographic distribution, but let me come into the case without going into the mathematical calculation. I am not into the variational part. So let me show what is the quantum leap is. What Alice and Bob gave from the photon basis, the digital data can't be traced by any eavesdropper who are present in the channel. That is called the robust security. So if send the same photon based on the Bell-State analyzer, the classical signal will be received. But the entangled photon, when it is saying, it receives and makes a transformation. So that means this is my Bell-State analyzer, send the same fit, receiver receives it, and this is the entanglement photon going through the same Bell-State analyzer. Receiver receives the transformed value and gets actual data based on the same basis. What is the photon analyzer basis? So teleportation transfers the quantum state of the particle, not the particle itself, so that your information is perfectly clear. So using quantum entanglement alongside with classical communication channels, we can transmit the quantum information across any distance, and this is called the flawless transfer of the quantum states, which is not possible in the classical electronics. So let me go into that teleportation in more details. We have a photon source. We have a photon source. We have a photon 2 and photon 3. Photon 2 sent to Alice. Photon 3 sent to Bob. Unknown source, I am sending another photon to Alice as a photon 1. So photon 2 and photon 1 are received by Alice, while photon 3 is received by Bob. So Alice send the Bell-State measurement performed between photon 1 and 2, which is the Bell-State analyzer I am showing here. Perform the Bell-State measurement between photon 1 and 2. Photons 1 information is entangled photon 2. Original state at this side is destroyed because it is already information is measured. Both photon is photon 3 and instantly collapses into a related state. So Alice obtained 2 classical bits because of the Bell measurement result and send those to Bob with classical, no need of quantum. Bob applies one of the 4 operations. What are the operations? 0, 0, 0, 1, 1, 0, 1. 0, 0 is for identify, 0, 1 is for Pauli X, 1, 0 for Pauli Z date, and 1, 1 for X date. Bob will get state of Bob. This is called psi. So look, entangled photon may be destroyed. What about the Bell state measurement Alice said from that the digital logic Bob will get back to. And through a classical channel, no cost of quantum hardware. So final outcome, original photon of Alice is destroyed. Quantum state only existed, Bob, no cloning occurs, information is transferred, not the matter. So this is, I am transferring information without transferring the matter. This is basically the quantum teleportation is for today's world. The quantum teleportation works in this particular matter. So now I am coming to the concept of the quantum machine. That is the last part of this. So I have developed this total slide in 3 parts. The fundamental part is the classical security and threat and how the quantum correction can help. Second is the development of the logic gate and corresponding the algorithm where this logic gate will work and how we will get the reduction of time complexity and data calculation as easily. Third part, I am moving from algorithm towards the machine learning where the quantum computers and quantum circuits to perform the learning task by inputting data into quantum sets and optimizing the state parameters. What are classification? One is the quantum data and quantum model, and another is the classical data and quantum model. Mostly we work on this, the variational quantum classification. What it will give it to you in a nutshell, if your regression will give you the 78% accuracy, VQ will give you the more than 8%. That's all. Same data set, less time calculation, less iteration, better accuracy. That's doable in a nutshell. So quantum style classical machine learning, it helps you to run on your classical computer. No need to go for GPUs or everything else. That is basically one of the examples. It's a tensor. So training time reduced. Gradient descent now replaced by the quantum tunneling, complex network topology, and can perform the complex tensor matrix. The privacy and security issues where I had started. The strengths processes large data at once. Superior computation power, improved predictive analysis. Weakness, obviously the significant challenges to existing security protocol demand extensive expertise. Opportunities, detecting and mitigating security breaches, precisely finance defense. New algorithms people are trying to develop. I am not going into the VQC details, but this is one of the research area people all over the world are working on. The threats of the cyber. Vulnerabilities. That's one of the major disadvantages of quantum machine learning. So the challenges of integrating quantum machine learning, data availability, algorithmic complexity, hardware limitation is a major factor. Integration factor, seamless integration, yet to be developed. So we are talking about the yet to be developed in seamless integration. Skill gaps. We are not the industry wants the skilled resources. We the engineering colleges can't provide the skills, supply, cost factors, very high cost, wider acceptance, limits. So these are my challenges in integrating it. The advantages, speed, obviously, accuracy, scalability. Large, expensive, larger data set with a very smaller time. Complexity can capture complex patterns and optimization. Solve optimization problem with less time. That Grover's algorithm. So these are quantum machine learning implements. Computational efficiency, I have already mentioned, superior optimized solution, fast computation, increased precision, scalable data analysis. So the difference I have already mentioned and QAOA, quantum approximate optimization algorithm. Without going into theory, I am going this calculation because time is also unlimited. QA normally used for max time. That is the full. Graph has, we know, suppose two vertices, V1 and V2, one edge between them. We have the objective to minimize the path. We can maximize it. We are using a two binary variables Z1 and Z2, which belongs to Z and 1. So max cut, what will be my cost function? Z1 XOR Z2. So if I use, it will give me the cut value, that is the XOR bit. Max cut, the Hamiltonian of the cost factor, the formula is half of I minus Z1. So that means if 0, 0 is 0 or 1, 1 is 0, that means 0, 0 and 1, 1 are aligned, 0 and 1, 0 are anti-aligned. These are my eigenenergy because I minus Z1. So 0, 0 and 1, 1 will be aligned, 0, 1 and 1, 0 will be anti-aligned. So if we apply Hadamard rates, then we will apply 1, so we will half of 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. You will get a unitary cost function that is given by the scientist at e to the power minus gamma of Hamilton. State Hamilton will be sum of x1 plus x2. That means the numeric values will be pi 2 and pi 3. I calculate it, maximize it, differential, then we get these two things. That means where they are aligned energies, those have the low solution probability. Where there are anti-aligned energies, they have high solution probability. That means it supports the X0 frequency. Now, to break 1 into 4 parts, where 2 are low and 2 are high with equal probability, one easy solution using Shannon-Stanford theorem is that low values are 0.125 and high values are 0.375. So, what will be my sum of the high values? That is 0.75. What are the improvement from classical concept? From 50% improvement to 0.5. For a two-node graph, my improvement is 0.2. That is the beauty of QAOA. So these are the algorithmic complexities people are using now. I'm going into the last. Now I am using the last part of my algorithm. So we are considering some 2D data points 1, 0, 0, 1, 1. My initial centroid, we are considering the 1, 0 and 0, 1 as usual. The quantum state, if I encode it, naturally, two values will be 0 and 1, no problem. But the hard value will be Hadamard 0 plus 1 by 2. So my centroid is 1, 0 means 0 and 0, 1 means 1. These are my centroids. The formula is x minus mu whole square. This is mu and this is x. So the formula is the basic of this formula, a square plus 1 minus 2ab. If I apply it, what will be the distance for x3? This is my x1 and x2. So my distance for x2 will be 0.707. These two centroids. And the value will be 3 minus mu square is 0.56. What the distance for x1, 1, 0, 0, 2, and distance for x2, 0, 1, 0. So, what will be my cluster? Please think. My cluster will be x1 will give this, x3 will give this, x2 will give this. So, this is the factor where 0.586, 0.707, these are very close. The x3 values. Now look, what are my values here? 1 and x1 of mu1 is 1, x2 of mu1 is 0, and x3 of mu1 is 0.707. So which are closer? 1 and 0.707 are closer. So my cluster is x1, x3, my cluster 2 is x2. So centroid we have updated 0.5 into x1 plus x3 and x2 is as usual. So 0, 1 will remain same. First one will be 1 plus 1 comma 0. So this is the quantum k-means. Instead of classical means, we are using the cluster formation by the distance means. What are the roadmaps? I am just last 2-3 slides of my discussion. 2024 we wrote some roadmap of algorithmic. 2025 the deployment. 26 is the procedure testing. 27 is the benchmarking. 28 is the industry association and 29 is the standardization. And that's why the leading institutes, not only the center funded institutes, but leading private engineering colleges started their UG and PG courses on this domain so that they can produce skilled manpower in 2020. Look, these two people, they got the 2025 ACM Turing Award. The blue person is Bennett and the red color is Bassard, recognizing for their role of establishment of foundations. Bassard is a scientist of computer science. The Bennett, scientist of physics. So role of science, pure science now determining who is going to get ACM. And what India has developed, this is the IIT Delhi campus. DRDO center, distance 1 kilometer communication, no noise possibility for intelligence. Seamless transformation. That data is published in 2025. This is IIT Delhi campus from one point to another point. 1 kilometer long distance quantum communication, 0 meters. That's where India is moving. My job is to just disseminate what the knowledge we have, and I want a few questions from your side so that we can move towards the for the next generation. Any queries from the participants? Any question, please? Am I audible? So, any queries, please? Actually, sir, already NPM starts to provide fund based on the your project proposal, and some of the private institutes also get fund on that. In West Bengal, one leading private engineering colleges also get fund and develop the photonic laboratories on that part. So it's maybe 4, 5, 6 years, and some leading engineering institutes, government funding institutes started there. So they have already developed laboratories. And if you can visit IIT Kanpur Physics Laboratory, sir, already developed a photonic bench where you will get a very good quantum entanglement demonstration in physical, and that is 2, 3 years back. So laboratory purpose already started, development purpose DRDO also started, and let's find out how this we can make. Sir, you may introduce few quantum basic level papers in their UG courses. If you are under university, then you can make a optional additional course, few MOOCs, you can guide them. So basic algorithm development, basic quantum entanglement, and you can give small projects on the quantum algorithms or quantum cryptography. Maybe BB84, F91, E91, E92, those protocols. So students can develop slowly on those particular scales so that they can proceed forward. So we can together, I am also trying in my institute, some other faculties in Kolkata, I know they are also trying to develop some sort of infrastructure. Maybe ultimately this combination may lead to some meaningful realization in next 5 to 10 years.
Sir, I am Abdana Munshi. I have a question. That
Yes,
what is the difference between quantum cryptography and post-quantum cryptography?
Quantum and madam?
What is the difference between quantum cryptography and post-quantum cryptography?
Post-quantum cryptography, madam, so far the quantum cryptography is basically modification of the BB84 is basically a quantum cryptography, and its modification of some vulnerabilities of BB84 in E91 and E92. E92 is mostly considered as a post-quantum cryptography where they can send a very large scale cube classical bit on a large scale distance. Both things without any interference, eavesdropping. Eavesdropping is practically zero. People are trying to achieve E92. You may search in Google. I have not gone through details of the quantum cryptography in this particular lecture, but E92 people are trying to go for that level. So maybe that may be considered post-quantum, but yet to be, these are in the nascent stage, madam. Right now, no one can talk that this is the post-quantum because the foundations. But IBM research has a wing. They are trying to have a few lectures in the YouTube in a found, and they are trying to move towards that direction. Any other queries, madam? Thank you, sir, for inviting
Thank
me
you, sir.
also.
Very nice session.
Thank you, sir. Please allow me to leave the meeting.